In this lecture, we will discuss the covariance and correlation coefficient of bivariate random variable. Also, the correlation and the covariance coefficient of independent random variable we will discuss in this class. First, let us talk about the expected value of random variable. For one random variable, we already know that the expected value of discrete random variable can be described by this formula, where x is the value of a random variable x and the p is the probability mass function of a random variable. So in the continuous random variable case, the expected value of a random variable x can be described by integrating the product of the value of this x is the value of a random variable x, and f sub x is the probability density function of a random variable x. We will integrate it from minus infinity to infinity. We'll get the expected value of random variable x. So in case of function g of x is the function of a random variable x, then its discrete, then its expected value for the discrete and the continuous cases can be described by this formula. Now let us extend this concept for the two random variable or for bivariate random variable. So e of xy is the expected value of random variable x and y, bivariate random variable x and y. This can be described by taking the summation with respect to x and y, and for the product of the value of random variable x and y multiplied joint probability pm of probability mass function of bivariate random variable x and y. So this is the discrete case, and similarly for continuous random variable x and y, their expected value can be described by integrating the product of the PDF of the joint PDF of random variable x and y with the values of x and y random variable and integrating them along x and y variable x and y. Similarly, the function of bivariate random variable, these formulas describe the expected values for the functions of bivariate random variable x and y. The expected value of is a linear, so by taking the expected value of linear combination a of x and plus b of y, so a and b are the constant here, some constant here, so its expected value would be a multiplied expected value of x plus b multiplied expected value of y. We already know the kth moment of one random variable, which is described by the expected value of x raised power k. The central moment, the kth central moment of x can be described by this formula, by taking the second central moment of variable x, which gave us the variance of random variable x. So let us extend this concept to the two random variable or for the bivariate random variable. Jth and kth moment of a random variable of bivariate random variable x and y can be described, which is the expected value of x raised power j and y raised power k. Thus jth and kth central moment can be described by this formula. So when j and k are both equal to 1, then this formula can be transformed or to the correlation of the x and y. So this gave us the correlation of x and y when j and k are equal to 1. So next, the covariance of x and y can be described like this. So by changing this central moment, jth and kth central moment, we transform it to the covariance of random variable x and y. So the covariance of x and y can be described the expected the joint expected value of x and y we can write this one, the covariance of a random variable x and y. So by expanding this formula, the right hand side of this equation, so I will get the expected value of xy minus mean value of x into mu of x into y minus x into mu of y plus mu of x mu of y. So by expanding this formula, this equation, I will get the expected value of the joint expected value, the expected value of xy minus mu of x expected into expected value of y minus mu of y into expected value of x plus expected mu of x mu of y. So by expanding this equation, I will get this mu of x into mu of y will cancel with one of the terms. So I will cancel with this term. Eventually I will get the covariance is equal to expected value of x and y minus mu of x into mu of y. So it is the covariance of bivariate random variable x and y. So when both random variable x and y are equal, so this formula, this covariance change into the variance. Now let us talk about independent random variable. Suppose if x and y are independent variable, we already know that for independent random variable, their joint PDF or joint probability mass function. So in this case, I am considering the continuous situation. The joint PDF must be equal to the product of the marginal PDF of x and then and the marginal PDF of y. So this correlation, I can write expected value of x is equal to integrating so the product of the marginal, so I can write it like this way. Already I have defined the expected value of x and y. So this joint PDF can be written in the product of the marginal PDF of x and y. So I can expand the right hand side of this equation like this. Now by separating these two terms, I will get the product of expected value of x and y should be equal to the joint expected value of x and y. So in this case, if x and y are independent, then their covariance must be equal to 0. If the covariance is not equal to 0, then I can say that hence the random variables are uncorrelated. Here the reverse is not true. If the covariance of x and y random variable is equal to 0, So it is not necessary that the x and y are independent. If however the converse is not true in this case, when covariance is equal to 0, it is not necessary that the both random variable are independent. Now let's move to the examples. An example: consider a joint PDF f sub x y is equal to x plus y for given range x is greater than x and y are greater than or equal to 0 and less than or equal to 1. So we have to determine the covariance of x and y. So the formula we have already derived for the covariance of bivariate random variable, which is the expected value of xy minus the marginal expected value of x and marginal expected value and into the expected value of y. So the expected value of x we can calculate by integrating the product of joint PDF of bivariate random variable with its product with the random variable x and integrate it from minus infinity to infinity for x and y random variable. So the given limits are from 0 to 1. So the right hand side we can write it as we will integrate from 0 to 1 along x and y axis for x and y variable. So by expanding this product we will get x square plus xy. After integrating this right hand side with respect to x, we will get 1 by 3 into x cube. So by incorporating the limits of random variable x, we will get this expression 1 by 3 plus 1 by 2 into y. Now we integrate with respect to y. So by integrating this expression with respect to y, we will get 1 by 3 into y plus 1 by 4 into y raised power 2. So by incorporating the limits, I will get the expected value of x, which is equal to 7 by 12. So by symmetry, the expected value of y is equal to 7 by 12. So how this is equal? So by using this expression, I mean by replacing x by random variable by y. So the limits are the same. Therefore the result, the expected value of random variable of y would be same as the expected value of random variable x. Now next, the expected value of x and y, we will integrate it. So we will integrate the product of xy with the joint PDF of xy. We will integrate it from 0 to 1. So by expanding this expression, I will get x square into y plus so here is a typo. I will replace it with the x. So the x into y raised power 2. So by first we will integrate it with respect to x. By integrating it, I will get x raised power 3 by divided by 3 into y plus x raised power 2 divided by 2 into y square. Now incorporating the limits, we will get this expression y by 1 by 3 into y plus 1 by 2 into raised power into y raised power 2. So again integrating it with respect to y, so I will get the expression. By plugging the limits, we will get the expected value of x and y is equal to 1 by 3. Now incorporating these, the expected value of x and the joint x and y bivariate random variable x y and their marginal expected values in this formula. So we will get the covariance, which is equal to -1 by 144. So hence x and y are correlated. Now let us move to another example. Here, suppose the joint probability mass function of bivariate random variable x, y is given as the joint probability is equal to 1 by 3 when random variable x is equal to 0 and y is equal to 1, when x is equal to 1 and y is equal to 0, and x is equal to 2 and y is equal to 1. Otherwise it is 0. We have to find Rx and y are independent, Rx and y are uncorrelated. So if these are uncorrelated, then we can say that x and y are independent random variables. So let us first find the marginal probability mass functions of random variable x and y. So when x is equal to 0, their marginal probability mass function is which can be defined by this way. Sorry, let me erase this. So when random variable x is equal to 0, there is only one possibility that y should be 1. In that case, so their marginal probability, which is equal to 1 by 3. So for random variable probability mass function for random variable x is equal to 1. In this case, y would be 0, so the marginal probability is 1 by 3, which is marginal EMF probability mass, the joint probability mass, so mass function is 1 by 3. So for x is equal to 1 and y is equal to 0, so the marginal probability mass function for x is equal to 1 by 3. So when x is equal to 2, so in this case the marginal probability mass function is 1 by 3. So incorporating here the so in this case the marginal PMF would be 1 by 3. The marginal PMF of y can be defined in this way. Here for y is equal to 0, the marginal probability mass function would be 1 by 3. Here only 1, and when y is equal to 0, x is equal to 1. So in this case, this joint PMF was 1 by 3. So by taking another case when y is equal to 1, in this case there are two possibilities. X could be a 0 and x could be a 2. So their joint, so their marginal probability mass function would be 1 by 3 for this case, and 1 by 3 when x is equal to 2. So we will add these terms together. So the marginal PMF for y when y is equal to 1, it is 2 by 3. So the marginal PMF of y is equal to 1 is 2 by 3. So here we have to find y, and x and y are independent. So for this case, their marginal their joint PMF probability mass function should be the product of their marginal probability mass function. So in this case, when x is equal to 0 and y is equal to 1, their joint probability mass function is 1 by 3. So this is the case. So the product of their marginal probability mass function is 2 by 3. Hence we can say that x and y are not independent. So they are independent. There should be some correlation in this case. So by taking the B part of this problem, so we have to find their correlation, and so the covariance can be defined by this formula. We already know. First we have to find the expected value of x. So which would be equal to, when x is equal to 0, it is 1 by 3. So when x is equal to 1, it is 1 by 3. When x is equal to 2, it is 1 by 3. So incorporating in this formula, so the expected value of x is equal to 1. So the expected value of y, so there are two possibilities. Y could be a 0 and 1. So when y is equal to 0, its value was 1 by 3. The joint PMF was 1 by 3. When y was equal to 1, so the joint, so the its marginal PMF was 2 by 3. So incorporating in this formula, so I will get the expected value of y, which is equal to 2 by 3, and the expected value of the x and y, that is equal to, when x and y are, x is 0, y is equal to 1, it is 1 by 3. When x is equal to 1 and y is equal to 0, it is 1 by 3. When x is equal to 2 and y is equal to 1, it is 1 by 3. So incorporating here, so 0 will multiply, this term will cancel out, this term will also cancel out. So in this term will only contribute when x is equal to 2 and y is equal to 1. This is equal to 2 by 3. So incorporating in the covariance formula, so we can say that x, so here the covariance is equal to 0. So we can say that x and y are uncorrelated. But in this case, x and y are not independent, as we have already discussed that when x and y are independent, then there must be the covariance is equal to 0. It means that x and y are uncorrelated when x and y are independent. However, the converse is not true, as in this case. Now let us move to another example. In this example, consider a binary communication channel as shown in figure here. The channel input symbol x may assume the state 0 or state 1. So here is the state 0 and here is the state 1. And similarly, the channel output may be symbol symbol y may be assumed state 0 and state 1. Because of noise in the channel, the output 0 may convert into output 1. Sorry, the input 0 may convert into the input 1 and vice versa. The channel characterized by channel transition probabilities P0, Q0, P1 and Q1, where P0 is equal to 0.1. So this shows that the probability that 1 will change into 0 will change into 1. So this is the probability of P0, which is 0.1, for the probability of P1, which is equal to 0.2. Also P0 plus Q0 is equal to 1 and P1 plus Q1 is equal to 1. So we have to find the mean and the variance of random variable x, find the mean and variance of random variable y, find the covariance of random variable x and y, find the correlation coefficient of x and y. Here the joint probabilities of when x is equal to 0 and y is equal to 0, that is 0.45. The joint probability of x is equal to 1 and y is equal to 0, that is 0.1. So x is equal to 1 and y is equal to 0, this is 0.1. The joint probability of x is equal to 0 and y is equal to 1 is 0.05, and the joint probability of x is equal to 1, y is equal to 1 is 0.4. So first let us find the mean and variance of random variable x. So the expected value of x can be defined as this formula. We already know when x is equal to 0, the probability is its probability is 0.5, and when x is equal to 1, its probability is so that is also 0.5. So the overall expected value is 0.5 here. Is similarly the variance of random variable x, which is defined by this formula. So the second movement of x is defined by this formula, which is equal to 0.5. So this way we can find the variance of x by incorporating the above values in this formula. We will get the variance of x, which is equal to 0.25. The mean and the variance of random variable y can be found in this way. The expected value of y, which gives the mean, by implying the formula for the expected value of y. So we will get the expected value of y, which is equal to 0.45. So when y is equal to 0, so it's from here you can find when y is equal to 0, there would be the two possibilities. This could be 0.45 plus 0.1. This would be, so the joint probability would be 0.55. So in this case, when y is equal to 1, the joint probability is 0.45. So incorporating here, so I will get the expected value of y is equal to 0.45. So the second movement of y, which is 0.45. So by incorporating in this formula, I will get the variance of random variable y, which is 0.2475. So next, the covariance of x and y. So first we have to find the expected value, combined expected value of x and xy. When x is equal to 0 and y is equal to 0, this probability was 0.45. When x is equal to 0, y was 1, so the joint probability was 0.05. Their product will be 0. When x was 1 and y was 0, their joint probability was 0.1. This term will eliminate. When x and y both were equal to 1, their joint probability was 0.4. So the expected value of the joint expected value of x and y is equal to, so this value is equal to 0.4. So incorporating the covariance formula of xy, so by incorporating these values, so I will get the covariance is 0.175. So hence I can say that x and y are correlated. So the correlation coefficient is defined by this formula. What we will do, we will divide the covariance by the sigma x and sigma y, the standard deviation of x and standard deviation of y. So by plugging these values in this formula, so we will get correlation coefficient of x and y, which is equal to 0.704. That's it.